Welcome back. In the last video we have seen how to define Laplace transform for an absolutely integrable function which is a smooth function rather, because we have used Fourier integral theorem to define this Laplace transform. So the function f of the function f has to be piecewise smooth or because we used only f of x on the left hand side in the Fourier integral theorem. So it's what you expect is a smooth function, that means it is a continuously differentiable function, or at least differentiable function, a differentiable function with only it is a differentiable function, and that is absolutely integrable function for which you have this Fourier integral theorem is valid. So you have defined Laplace transform for such a function f. So you have, so in the way you modified this integral theorem, what you end up is the function for which you have defined a Laplace transform is not just absolutely integrable function and differentiable function or smooth function. It is rather it is a much bigger class, such as including those functions plus any function of exponential order. And also we have seen if such a exponential function, for example here if it is a function of order a, in the inverse transform what you have is inverse transform. So in the inverse transform you have integral over contour c minus I infinity to c plus I infinity here, like here. So that is what is c? C is actually a real part of s, this variable s, that is what you have seen yesterday. So that c has to be bigger than a because your function is absolutely integrable function, and because the way you have seen fx into e power minus ax, that has to be for that is going to 0. Okay. So e power minus cx into fx that goes to 0 implies fx has to be a function of exponential function of order a is less than c. So in that sense c has to be greater than a. So this is how you define this Fourier Laplace transform and its inverse transform, and clearly because f is a smooth function, that is what we considered. So you have this fs is actually unique function. So this Fourier transform, suppose you have f bar of s that is there for two different functions, f1 of t and f2 of t, then this once you have this Fourier transform, same Fourier transform for each of these functions, implies f1 of t has to be equal to f2 of t. So this is uniqueness of Laplace transform. So if you take two different functions, if they are smooth continuous functions, so you can easily see that this is you can easily see, because if it is the same and you have f1 bar of s is same as f2 bar of s, that implies integral 0 to t f1 of t minus f2 of t times e power minus st dt equal to 0. Rather this is going to be infinity. Okay. And then that implies the inverse Laplace transform of 0, the right hand side is 0, is equal to f1 of t minus f2 of t. But we know that inverse Laplace transform of 0, if you take Laplace transform of 0 is 0 which is a function of s, that is also 0. So this implies you can say that this is inverse transform 0 itself is 0. Okay. If it is if you are looking for only continuous or smooth functions which are differentiable functions is 0, so that makes it f1 of t equal to f2 of t. So that way, in that sense, these two are unique. If you have for two different functions, if your Laplace transform is unique and these functions are piecewise or continuous functions, rather at least continuous functions, that is enough, then it has to be equal to this. Okay. But the way we have defined, they are actually the way we started, they are actually piecewise, they are actually smooth functions, that is at least differentiable functions, once differentiable functions. So you have a uniqueness of this Laplace transform. Okay. And so existence of the Laplace transform also you can talk. rather you cannot say this is the uniqueness of inverse transform, basically inverse Laplace transform. Okay. So, we can also show that if f is exponential function of order a, then you have exponential of order a, you have this Fourier transform is defined. So, we will show that it actually exists. So, let me write it as a result. So let me write it as a result, small result. So, you have if f of t is continuous function in every finite interval 0 to t, okay. So, t is positive and is of exponential order, is an exponential function of order a, let us say, then that is e power a t. F of t is e power a t. Exponential of order a means say, okay. So, let me not write it. So, then Laplace transform f bar of s exists. So, this is, we can easily see, provided a real part of s has to be bigger than a. So, this is what we have seen already. And how do we prove this? Let me do small calculation so that you can easily see this. So, if you do this, f bar of s, if you define, by definition this is, so the way we have chosen, if it is if actually f is a smooth function, so that makes it is continuous. So, that is a sufficient condition, basically this is. So, f bar of s, what we have actually has what we consider the function is, that is smooth function, this is more than continuity. So, such functions 0 to infinity f of t times e power minus st dt. So, you want to just take the modulus of this will be less than or equal to 0 to infinity e power minus st, that is positive quantity, and then let's time being assume that s is a real. For real values we are only looking at the real values, then this will be simply this with modulus, this is this, if s is real, into modulus of f of t dt. This will be less than or equal to what you have is f of t at infinity 0 to, so at infinity this is like once this is a function, exponential function of order, and what is your f of t is basically some constant times e power a t, that is how it looks, okay, at higher values. So, and actually this is true as t goes to infinity, okay. So, this is actually f is equal to this as t goes to infinity. So, you want to be rigorous. So, what you do is 0 to some fixed quantity, let us say t naught into e power minus st mod f of t dt plus t naught to infinity e power minus st. In this case, for bigger values of t sufficiently, t naught bigger, so you can write this as k times e power minus a t. So, you can write minus s minus a dt, and this is because f is a continuous function, and this is well defined, this is finite quantity, and you have a fixed quantity k, and this is also finite quantity. So, together it is a finite quantity, and where is it valid? S is, if s is bigger than a, that is true, that is valid, okay. So, as of now, because we have not taken the modulus for this when s is complex, so for real valued this is true. So, once you have this real value, f bar of s real value, it exists, Fourier transform exists, s greater than a, for example s beyond this it exists, by you can extend this as a analytical continuous. So, this function as such, this one can show that we do not give the proof, this Fourier in Laplace transform is actually analytic function in the as s greater than a in the as s greater than a, that means in this region this is analytic function. So that is a theorem that without proof you can assume, and because see this calculation you have done for s real, s greater than a here. So because it is analytic function as such, so we can see that that is an independent result that it is an analytic function. Because it is analytic function, once you know this this exists here, you can extend analytical continuation, you can have the analyticity everywhere, so that this is the Fourier transform exists everywhere s greater than a, even if s is complex. Okay. So this is how you show that this exists, existence of, this is the existence of Laplace transform. Okay. So now we have so for a bigger class of functions, we have Laplace, we have defined what is Laplace transform and its inverse transform. These are unique, because the moment you say this is inverse, the way we define, once we call it inverse, that means its mapping is unique. So you have a unique from here, from the domain to codomain, codomain to this, it is unique function both sides, so that it is a mapping from space of functions, this is exponential bigger class of functions, to this analytic functions f bar of s side. Okay. So let us compute for elementary functions what is your Laplace transform. So let us start with simple examples for which we can calculate the Laplace transform. So start with let 1. So if my f of t equal to 1 for t positive, then what is its Laplace transform? F bar of s, by definition 0 to infinity, f of t is 1 times e power minus st dt. This is exponential of function of exponential order 0. So you can expect this minus e power minus st by s 0 to infinity. If you do, you get this is 0. This infinity when you put, because t is t equal to 0, t equal to infinity, and only when s is positive. Okay. Because this is a function of exponential order 0, so this has to be, real part of s has to be 0, has to be positive. That is why this quantity at infinity is 0, and minus minus plus, when you put t equal to 0, this is 1 by s. Okay. So this is exactly what you have as your Laplace transform. So immediately Laplace inversion of 1 by s is actually 1. So this is what, so if you calculate for a certain function which you already a priori you know, you calculate its Laplace transform, and so what is the resulting Laplace transform, for which if you just write its inverse, is actual function you started with. So that way inverse Laplace of 1 by s is 1. The second thing we can consider is we have already seen what is f of t is. This is exponential function of order 0. If you consider exponential of order a, for which Laplace transform, if you calculate, f bar of s is 0 to infinity e power a t times e power minus st dt. In the same way, you can see that is going to be 1 by s minus a, real part of s has to be greater than a. So inverse Laplace transform of 1 by s minus a. So whatever s, 1 by s minus a, you can immediately write this as e power a t. Okay. So this is how it is. Okay. This can be even a can be even a negative number. Let us see if it is a negative number, what happens. It is going to be 1 by s plus a, real part of s is greater than minus a, you have to write in that case. So this basically you have your analytic function will be, the integral can be even, you can think of just over positive. Okay. Anything you can choose here or anywhere greater than minus a. So if it is minus a here, anywhere you can choose as your c minus I infinity to c plus I infinity. So that way, so you can see that this is actually valid for every a belongs to minus infinity infinity. Okay. This is the case. So this is a. So the third example that you can do is you can think of polynomials, exponential functions you have done, simple functions. Now you can think of polynomials. F of t is, let us say, t power n. N is for that matter any alpha belongs to a real number. So if I take like this, what is the Laplace transform? So this includes if alpha is integer, positive integer or negative integer, whatever. So if alpha is integer, so you can have, if alpha equal to 0, 1 we have seen already. So you have 0 to infinity t power alpha times e power minus st dt. So this will be how do I evaluate this? This is equal to, if I choose let s of st equal to, let us say, x. If let st equal to x, then s dt equal to dx. So this implies f bar of s. What you get is t is this is going to be 0 to infinity. T is x by s power alpha e power minus x dx is dt is dx by s. This is what you have. So this is equal to 1 by s power alpha plus 1, and you have this integral x power alpha e power minus x dx. So this x power alpha I can write like x power alpha plus 1 minus 1. So if you write like this, this is actually the definition of gamma function. So gamma of alpha equal to integral 0 to infinity x power e power minus x into x power alpha minus 1, okay, dx. So this is the definition of gamma function. If you define like this, where is this valid? This is actually valid. So if you look at only real line 1 2, so 0 to 1, except 0 if you put alpha equal to 0, this is 1 by x, this integral will be infinite in that case. So at this point it is not defined. If it is alpha is between 0 to 1, it is well defined. If alpha equal to 1, it is well known. And so how do I do this? So I try to you try to calculate gamma alpha plus 1 you consider. So you have integral 0 to infinity e power minus x power alpha minus 1 dx, x power alpha in this case. Do the integration by parts, so that you have minus e power minus x into x power alpha, put the limits, and this minus minus plus, and you have alpha times x power alpha minus 1 e power minus x dx. So what you have, this quantity, because of e power minus x this is 0, and because of x power alpha is yeah. So here alpha has to be, let us use alpha is positive side. So it is not alpha is positive. If alpha is negative, you can see that this is not at 0, it is not 0, okay. So actually negative side you can go up to, let us say, minus 1, okay. So anyway, we will see, we will fix this alpha is r. Actually you cannot define this one for 0, minus 1, minus 2 and so on. So that is exactly we will see here. So if alpha is let us say any number, if alpha is positive, okay, let us choose alpha is positive. If alpha is positive, that means here, okay. So you have this is 0, this quantity is 0. So you have end up as this is the definition of gamma alpha. This is what is true for. So this way you can go on this side. So 0 to 1 it is well defined, 1 to this side positive side is well defined. to get the negative side you use this relation to get gamma of alpha equal to 1 by alpha times gamma of alpha plus 1. So, using this, if I choose minus 1 which is not defined, if I choose any value here alpha, if you take this as alpha, and this is your definition of you define this as using the values gamma alpha plus 1, this is alpha plus 1 will be somewhere here. Okay. If it is close to here, alpha plus 1 will be here. So, at this it is already defined, we know. Okay. So, that is how you define all the values in between this. So, that way you have all the negative side minus 1, minus 2. So, once you have the values here defined in between, you can using them you can assign them for this here, like that you can go on getting it with 1 by alpha, of course. 1 by alpha times the values here will give me the values here, like that you can go on defining except 0, minus 1, minus 2 and so on. So, outside that you can use your you have this gamma function is defined. So, because I choose such a alpha, so now this integral is a gamma function. So, that is 1 by s power alpha plus 1 gamma of alpha plus 1. Okay. So, gamma of alpha plus 1 is actually if alpha is integer, one can easily see that you can go on using it. If alpha is equal to n here, using this gamma of n plus 1 will be n times gamma of n, again n into n minus 1 into gamma n minus 1. Again if I reuse, keep on using it recursively, what you end up finally is n into n minus 1 and so on, finally gamma of 1. So, gamma of 1 is, if is gamma of 1 is alpha equal to 1. So, that is e power minus x integral, that is actually 1. So, you have 1, that is n factorial. So, this is the Laplace transform of any general alpha such that alpha is cannot be non-negative. Okay. It's not it's all integers except all real numbers except these negative integers including 0, for which you have this is the Laplace transform. If alpha equal to n, so Laplace transform of this equal to 1 by s power alpha plus 1 times you have n factorial. Okay. Of course, real part of s is what is this exponential function, real part of s is so nothing is real part of s. What is the real part of s? T power alpha. What is t power alpha? If because where is this valid real part of s? To see this, you look at the x power alpha into, is it exponential order? That means this should behave like this into e power some minus ax, okay, times this limit. What is this limit? Limit x goes to infinity is always goes to 0 for every alpha, okay, including 0. So, if alpha is 0, this is going to be 0 for a positive. Okay. If a is positive, exponential any a positive. Okay. And you can see that if you choose this as your fx and you multiply e power minus ax, and this limit is always going to 0 as x goes to infinity for every x, okay, for every alpha. Alpha is, even if it is a positive bigger value. So, because of the polynomial kind of x power alpha divided by e power minus a alpha, we will go on if you keep doing it, you will end up with this if you differentiate many times by using L'Hospital law, it will come down, finally at infinity is going to be 0. So, that is how you can show that this limit is 0. So, that implies this function x power alpha is exponential function of order certainly of something less than or order less than a, of order let us say b, where b is less than a. A itself is true for every positive. So, that implies exponential of order 0. So, that implies x power alpha is exponential function of order 0. Okay. So, that means this has to be greater than 0, real part of S has to be 0. So, that is how we derive this, you get this Fourier transform of this. Here also same way, real part of S is positive. So, immediately you can write the inverse Laplace transform of n factorial by S power alpha alpha n, this is n plus 1 is equal to x power n, okay, or rather here t power n, or inverse Laplace transform of gamma and alpha plus 1 by S power alpha plus 1, which is equal to t power alpha. Did I use t power alpha? Yes, where alpha belongs to r minus 0 negative integers including 0. That is it. So, you have this result. Then we can go on next example. We can see that it is going to be let us use trigonometric functions. If f of t is a sine function, sine at, if this is sine at, a is real, a is a real constant, real number. If a is real number, then what is its this is also exponential of order 0, because if you multiply anything same way, this e power minus x minus ax, any a positive, multiply with the sin x, that as x goes to infinity, that is going to 0. So, it is exponential of order 0. So, real part of S has to be 0 when you define, once you calculate its Fourier transform. So, Laplace transform of this is equal to 0 to infinity sin a t times e power minus s t dt. So, this one you can write this as an exponential function. So, you get 0 to infinity e power I a t minus e power minus I a t divided by 2i times e power minus s t dt. So, this is equal to 1 by 2i times integral 0 to infinity, first integral is e power t times minus t times s minus I a minus integral again 1 by 2i, that you can put it as a bracket. So, here I have integral 0 to infinity e power minus t times s plus I a dt So, this is equal to 1 by 2i. What you get here is the value 1 by s minus I a, and here 1 by s plus I a. So, if you do this calculation, so s square plus a square in the denominator, and here s plus I a minus s plus I a. So, you have 2 I a. So, that is 2 I a, and you have 2 I, that gets cancelled. So, you end up getting a divided by s square plus a square. So, this is another way of evaluating this integral by you can write sine as in terms of exponentials and use the integral directly. You see this. Okay. So, of course, here real part of s is positive because it is bounded functions. All these bounded functions are exponential functions of order 0. So, same way you can get this cosine function also. So, if you write this cosine function, so what is the Laplace transform of if let us write this, f of t is cos a t, a belongs to r. So, for which if you write same way f bar of s, this is 0 to infinity e power minus s t cos a t dt. This you can easily see that s divided by s square plus a square. So, again real part of s is positive. So, if you see this as your function of s, anything like constant by s square plus a square bar or s by s square plus a square, inverse Laplace transforms is either cosine or sine. Okay. So, that is how you can see. Similarly, you can also work with hyperbolic functions, sine hyperbolic functions and cos hyperbolic. Sine hyperbolic of at, which is the maximum. This is of exponential function of order a, because it is e power at minus e power minus at by 2. So, this is a maximum of order a. So, exponential of order a. So, f bar of s, if you do the calculations routinely, sine hyperbolic at times e power minus st dt 0 to t e power minus at plus at minus e power minus at divided by 2 times e power minus st dt. This is equal to 0 to infinity e power. So, I will write directly. So, 1 by 2 times 1 by s minus a, and the other one is 1 by s plus a. So, this will give me s square minus a square, s plus a minus s plus a. So, you have 2a. So, you have a denominator 2 to 2 goes. So, you end up this one. The real part of s is bigger than a. Similarly, you can also get f of t is cos hyperbolic. Cos hyperbolic at a is any real number. So, for this f bar of s, you do the similar calculation. So, you can see that s divided by s square minus a square. So, you observe that if it is plus, it is cos or sine. If it is a minus, in the denominator s square plus s square minus a square, you have cos hyperbolic or sine hyperbolic. Here real part of s is bigger than a, because cos hyperbolic at is e power at plus e power minus at divided by 2. So, this is exponential of order bigger one, this one, okay, order a. So, that is how you can get these elementary functions, its Laplace transform and its inverse transform as well. Once you know the transform, inverse transform is of this one, s square minus a square is equal to cos hyperbolic at. Here inverse transform of this is inverse transform of this one, a divided by s square minus a square. This is sine hyperbolic at. Like that you can get. So, we can go on different some complicated functions. We can also derive, we can also calculate Laplace transform of some complicated functions. For example, Bessel functions. You can also construct, you can also calculate the Laplace transform of some what is that error function, some special functions. Okay. So, before we do that, we'll just what we do is as and when we apply the Laplace transform, when we do the applications, as and when it is required, we will calculate the Laplace transform so that its inversion, so that you calculate. So, when you calculate the inverse, if you see these functions, then you can directly write as its inverse Laplace transform. Otherwise, there is a way to find the inverse Laplace transform that we will see in the next few in the next videos. And before I close today, so what we do is you see that the way we have defined Laplace transform, f bar of s equal to integral 0 to infinity f of t into e power minus st dt, okay, where f is exponential function of order, some order. Okay. And what you have seen that this exists if f is a continuous a smooth function with absolutely integrable, or exponential function which is smooth, for which this exists. That is what we have seen in the early in the starting of this video. We have seen that this exists, and also you can see that limit f bar of s as s goes to infinity, what happens to this? If you consider this, and you can easily see that the right hand side we have derived earlier, that this is so from this one can show that so this is with this one can show that from this you can easily see that this is going to be plus k times 1 divided by s minus a times e power t naught times minus t naught times s minus a. T naught is bigger T naught here. So, this is what you have. For this one is some constant, but here also if you once you get this. So, because if it is a continuous function, because f is continuous function, this is some bounded. So, e power minus st integral, you will have e power minus st naught divided by minus e power s at 0 it is 1 divided by s minus s. So, this is what you have. So, this goes to 0 as s goes to infinity, that is what you can easily see. Okay. So, because of this we can remark that this is as s goes to infinity, this is 0. So, if f of t is rather smooth or continuous function, continuous and exponential function of order, okay, and exponential function of some order. This is what we have. If it is a function of exponential function of some order and is continuous, this has to be 0. From which if f bar of s, for example, if this is simply, so let us say s, clearly if this is the case and you have this result limit. Okay. Suppose if I have this one, then limit since limit s goes to infinity, this f bar of s, this is infinity. If I choose this, what we have is f bar of s is not a Laplace transform of any continuous function, any continuous function. Okay. So, not just s, or you can also write s square, any s square, this is true, s or s square, s cube, any polynomial in s. You can see that this is not Laplace transform of any continuous function. This is what we can conclude from that existence result. If f of t is e power a t square with a positive, then you can see that f bar of s, this is if Laplace transform exists, if it is this is a continuous function and it is, and what we have is not exponential function of some order, clearly it is not, because if it is exponential of some order, let us say b, then some b e power t square into this function into e power, if it is exponential function of order b, then I have minus bt. This limit has to go to 0. Is this really true? But this is not. Okay. This is actually limit t goes to infinity e power a t square minus bt. So, t square grows bigger than t. So, as t goes to infinity, this is going to be infinity, which is not equal to 0. Okay. If you have, if it is a function of exponential function of some order, we know that this result is true, this limit has to go to 0. Okay. And you see that this because this is not exponential function of some order b, some order, clearly because this is infinity, we cannot say that this integral Laplace transform e power a t square e power minus st dt does not exist, because this is exponential order which is higher than this is. So, its growth is bigger. So, that is why it is for any s, for any s this is going to be infinity, at infinity as t goes to infinity, which is infinity. So, this integral does not exist, okay, because of this result, because of this. So, e power minus bt, instead of b you take some s, s can be anything, you fix your s as any s this is true, for any s, for every s this is true. So, implies this does not exist, this is actually infinity. So, that implies f bar of s does not exist for the function for e power a t square, which is continuous, but not exponential function of order, some order. Okay. So, in the next video we will see some of the properties of these Laplace transforms, and we will state them, and we will just prove those properties, and then we will try to prove some applications of this Laplace transforms, okay, in the next later videos. Okay. Thank you very much.